could have made it if you would have left at 3 in the morning. It's a 6-hour drive. That's what I said, you could have made it.
Meanwhile, optimization. There were area optimization, volume optimization. There was, remember the oil line, pipeline, or in a pipe somewhere type optimization. There was a business one where you're optimizing profit, revenue, cost.
Well, I don't like to make fun of
Do you want to do some of the ones that are on here? Or do you want
No, do a different one.
You are so different than every other class. Of course, anytime they can get me to do some of them, they don't have to do it. So different. It's such a pleasure. Thank you.
Yeah.
After school, we're probably not going to leave until at 11.
We already got a couch study date.
When?
Okay, that's good. That's good.
No, but I would have liked to.
Only girls. It's only girls. If you bring food, you're after no. I don't think you're being hired. I think it's
I was going to say, you sound like a little sexist here, guys. You're not letting the gentlemen join your studies group. All right. What kind of a problem do you want? Area, volume, pipeline, what do you want? The tricky one? Okay, well then, number one, okay, well actually, I don't know. Volume is volume where you have to minimize the cost, but many of you did that on your project when you optimized your cost for something in your project. Not all of you did it, so you want a volume or not? Because that's the one that messes up. Okay. I don't dare make this up off the top of my head or we'll get something horrendously awful as an answer. So, where was I? I just saw it. Hang on. Back page. Ooh, that's kind of cool.
We got it. We only have 2 more purple days left.
Woo! Don't want that one. Ah, there we go. All right. I am abbreviating this. You have a closed rectangular container. It has a square base. Its volume is supposed to be 2,250 cubic inches. Okay. The top and bottom cost $2 per square inch. Wow. The side somewhere, I just lost my problem. $3 per square inch. Find the dimensions that will minimize the cost. We need a cost formula. Probably helps, usually, if you draw a picture.
What's that inches, the top and bottom, 2 inches, really right above the inches?
Here?
No.
Here?
What's that?
$2 per square inch.
Nothing?
That's per square inch. $3 per square inch. That's per. Okay. So, we are drawing, it's got, the key thing when you draw it, it's got to have a square base. But don't, since we know the height is not the same, do not draw a height that is the same. You don't want to make assumptions. All right, so what would you like to call the sides of these boxes? What variables would you like to use? Okay. But, do we need 3 variables? It's square base, so what would you like to call the sides of the base? It's a square. S's? Seriously, you want S's? Sometimes we think S's are 5.
Go with T's.
You can go with W's, you can go with X's. X, okay. But the height has to be something different. It's,
H.
okay. So, cost equation. Why does it say the costs are $2 per square inch? You're doing area. It's square inch, so you have to know the area. In this case, if the top and bottom are $2 per square inch, we need to know the area of the top and bottom. So what expression is going to give you the area of the top and bottom? X squared is one of them. I have a top and a bottom, so there are two of them, and then their cost is $2. I'm going to have 4x squared out of that deal. Then I have to do the sides. Are all the sides going to have the same area? Since it's a square base, yes, they're all going to have the same area. So area is going to be x times h, and there's 4 of them, right? You got 4xh, but you got to times it by how much it's costing you for those. So in reality, we're going to end up with 12xh's. Okay. Is that the only equation you need? Well, how many variables are in the problem? You got 2 variables, you got to have 2 equations. So we need, yeah, right, we'll need to change the h into x's so we have all x's, so we need another equation that has x and h in it. What other piece of information did they give you here? The volume is 2,250. That's going to give me 2,250. I'm going to need help here, dudes. 26. 27,000 even? Okay. How many x's are left? Yeah, we got 1 x on the bottom. So, okay. Looks a little funky. 4x squared, 27,000. And then, yeah, here's the question. How do you want to optimize?
That's the equation that starts, isn't it?
Yes, this is the equation that started. It's the one simplified. It's all one variable. This is now your original function. It's all one variable. It's simplified. This is the one we're trying to optimize. To find critical points. Since you find critical points, you do the derivative and solve the derivative. So, okay. This isn't too terrible. That's going to be 8x. I'm going to have to bring this up as x to the negative 1. So I'm going to have negative 27,000 x to the negative 2, which would actually, can I drop the x to the negative 2 back to the bottom? I'm going to have an x squared. I need more board. And then you need to solve it. So, okay, now it's algebra. How do you solve for x? Okay. That's fine if you all want to. If I was me, I would move the negative 1 over, make it 27,000 equals if you want to move it that way. One way or the other, you got to get rid of the fraction. So I'm going to end up multiplying x squared to the other side, which is going to give me 8x cubed equals 27,000. And yeah, we're going to divide by 8. Of that shape, how large or small could it be? You need an interval. How small could x be?
0.
Can it be bracket or parentheses 0? Parentheses. If you can't equal 0, you wouldn't have any volume at all. So that can't be. And then, how do I find how large it could be?
If it's 2 multiplied, it's infinity, right?
If it's 2 multiplied like this, x squared h, then yes, it's infinity. If it's not multiplied, if you have something plus something, how do you figure out your... You're trying to, like in this case, we're trying to maximize x. So if it was something plus something, if you want x to get big, that means you need h to get... So you put 0 in for the opposite variable and solve it, and that'll tell you how big x can get, if you need it. So since this one's parentheses, what do I have to do? I do a limit on it, yeah. So I'm doing limits of which function? The one we started with, yes. So I'm doing the limit as x approaches 0 of this lovely function. Which, okay, putting 0 into the first part, we're going to get 0. But what happens when I put 0 in the second part? Undefined, which is infinity. It's a positive number. So, yep, it's going to positive infinity. Is that good or bad here? That means we can't have a what? One more minimum. Yeah, we have no maximum, but we're not trying for a maximum. We want to minimize cost. So, fine, we don't have a maximum. It's going forever. That's okay. And then, of course, if I do the same thing and I do the limit on the function going to infinity, if you haven't noticed, these tend to have a pattern. Fine, I put infinity in there and square it. It's infinity, but the other piece is going to be 0, and I'm still going to get positive infinity. And is that enough proof? No. You have to prove that your critical point is a minimum. It has to be lower than those. So you need your critical point to test out lower than infinity. So you plug that into the original function too, and if we put 15 in this, we're guaranteed we're going to get something less than infinity. 900 over ooh. Okay, fine.
You put 15 in the what?
Into your original function. Same one. Same function you're doing the limit sign. You're putting the one right before the derivative is always your original.
So if they're both infinity, we use that to put in that.
Because you're testing that function to find the maximums or minimums. And so your maximum or minimum either has to be at the end point or it has to be at the critical point. So you're testing all things on the same function. Everything. If you get numbers with the limits, okay, then in this case, if the limits that come out to be numbers, your critical point has to be lower, because we're wanting a minimum. You would have to have a critical point that comes out lower than the limit should. If you didn't, you don't have a solution. Yes? Thank you. Okay, so in the end then, you need to answer the question. And the question was, what dimensions should the box be? So x is going to be 15. Yeah, and you actually have it. You have right here, you have h equals. So you can just go, oh, well then h is going to be 2250 divided by 15 squared, which is 225, so it's going to be 10. I can do that one. So our box would be 15 inches by 15 inches by 10 inches. And you have optimized. Woo, and I'm now stopping this, and we may never